That's fine.
Let me just get these quick because it's hard to see. Taylor, did you watch? Alright, you do that. That's really cool. I broke it. Alright, we'll just temporarily. Okay, so there's three types of reactions, three types of order. So three types of reaction order. So there's three types of reaction. Every single chemical reaction we've ever seen or done, well, that's just a lie, but basically falls into these three categories. There's and I'm going to write the first one on the left, and then the second one and the third. So do the same thing in your notes. Kind of go across the page here. And then underneath each one, so I'm going to title it, I'm going to write the rate law, and then the graphs. So there's a rate law and graphs you need to know for each one. So I'm going to just lay it all out now, then we'll go through practice problems on how to do it. All right, so zero order is the first type of reaction. First order is the second type. And second order is the third type. Now there's more than this. Okay, this is just what we focus on in AP. There's fractions. There's like 1.5 orders and 2. There's third order. There's more complex reactions, and you don't know what this means yet. I get that, but we just focus on these. Okay. So if we're going to write a rate law for a zero order reaction, so first let me kind of give you a generic formula or equation for each one. So zero order, let's say, is A yields B. First order, there's a lot of different ways we could write it, so I'll just try and keep it simple. It could be A yields B. It's A plus A yields B. Alright, so we can do that. And then this actually could be the exact same thing. Yeah. So, the equation doesn't affect the rate law, the experimental data does. And again, I'm doing this backwards, so we'll see how this works out. So you're a little confused. You're super confused right now. You're just kind of writing down what I'm telling you to. I get that. You're not really making sense yet. But so this would be like, H2O2. Or no, this could be, I'm trying to think of an example off the top of my head. You have one reactant, one product. I can't think of something off the top of my head. But this could be like the formation of water. This could be the formation of ammonia. All right. So these are actual reactions. I'm just giving you a generic formula for it. So the rate law for this would be rate equals K times the concentration of A, because it's always rate constant, which is K. We'll talk more about that today. Times the concentration of your reactants. Now, if there's only one reactant, then there isn't a B, right? And then in the book, there's A plus B yields C plus D, right on that page right in front of you. I'm just doing this a little different. But zero order means the exponent on A is 0. That's what that means. And I suppose, actually, for zero order, I could do A plus A as well. I could do that. In that case, it would be A times A, both raised to the 0 power. The point I'm trying to make right now, so start to make this connection, a zero order reaction, in a rate law, your concentration is raised to the 0 power. Again, I'm working backwards. We're going to do practice problems today, tomorrow, to help figure out how to write these and where it comes from. So it'll make more sense by the time we're done. Okay, I'll get to the graphs in a minute. This one, your rate law, I'm going to do the top one first. K times the concentration of A raised to the first power. Technically, you don't have to put the 1 there. You can just leave it. No exponent means raised to the 1. Okay, or if we're doing this one, it would be rate equals K times A to the first times A to the 0. Or rate equals K times A to the 0, A to the first. So first order reactions mean the sum of the exponents adds up to 1. So one of these must be 0. One of them must be 1. 1 plus 0 is 1. 0 plus 1 is 1. And I told you there are more complex examples. Technically it could be a half and a half. We don't get into that. There's not going to be on the AP test. I'm not going to give you anything with that. Once you see how to do this and you get good with it, hopefully by the end of tomorrow, maybe by the end of today you're sort of comfortable, but by the end of tomorrow, you'll see that even if we were to use halves, it's not that bad, but you won't see it. I highly doubt it. Good. So, if this is a 0, if your exponents all add up to 0, you could have A, B, C, D, you could have 5 reactants. If they're all raised to 0, that's called a 0 order. Same thing over here. You could have 5 reactants. If there's 4 zeros and 1 1, it's a first order. And if it's just one reactant and it's to the first power, it's first order. So that's all we're trying to learn right now. Is if you see a rate law like this, it's a 0 order reaction. You see one like this, it's a first order. So now second order, who wants to write it? Who's following the breadcrumbs here?
Rate equals.
Rate equals.
K.
K. Do this one.
The concentration.
Concentration of A.
Raised to the 2.
Very good. Raised to the second power. That's second order. Good. Or
Rate equals K. A to the 1. A to the 1.
sounds like a cheer. A to the 1. A to the 1. A1 steak sauce.
That stuff is good.
I used to eat that before I cared about what I ate.
Oh my god.
Read what's in there.
Put crap on my steak sauce.
Sorry guys. Maybe they've made it a little better, but I don't know. Like, even companies, take Kraft macaroni and cheese. They took out the weird coloring. Now they use like real food to turn it the orange color. You ever think about cheese doodles?
Yeah.
You should not eat anything that color. Just think about it.
The color orange?
That's really weird. No, it's like a neon fluorescent orange.
They're so good.
Moving on. Sorry, that's my thing. I'll go on tangents and rants. All right. Or who else? Someone besides Chi Chi. There's another way. There's actually 2 more ways to do it. I'm just going to do one more example.
A to the K.
Rate equals K times. Yep. To the 2. Very good. All right. So now, again, I'm kind of giving you the overview of each type of reaction. Then I actually have graphs I'm just going to put up on the board because I just found that they're good images for you to see. And it relates all 3 of these. Before we do that, let's make sense of this. So, let's say you have some reaction, okay, and we actually do it in lab, and we have a way of measuring concentrations with probes. All right, and we find that this rate, so the rate that A forms B, or we could say the rate of decomposition of A and the rate of formation of B, has nothing to do with this concentration. Why does that make sense? Plug in a number for that. What are you going to get every time? 1. So what does rate really equal in a 0 order reaction? It's not the concentration of your reactant. It's this. So underneath that, I want you to write the concentration of reactants have nothing to do with the rate of the reaction. Okay? The concentration, so write that down. The concentration of the reactants have nothing to do with the rate of that reaction. That sounds almost impossible. So you're telling me if I have 10 pounds of a reactant or 0.1 milligrams, it's going to react with the same speed. That's contradictory to what we've learned so far. Typically we learn more particles, more effective collisions, more reactions, so that would be an increased reaction rate. Some reactions, that doesn't matter. I looked it up. I was like, give me an example of zero order. Because in the past, I've been so focused on just like, this is what you need to know for the test. I kind of skip over some of the like real questions. Like, what the heck? Give me an example. When do we see this? So I looked it up, and this is a good example. If people take drugs for whatever, high blood pressure, diabetes, or whatever, some drugs will decompose at the same rate, irrelevant or regardless is a better word, regardless of the concentration. So if you take a 10 milligram pill or a 5 milligram or a 20 milligram, it will still decompose at the same rate in your body. So let's say let's see, what's the example they used here? For example, 10 milligram of a drug may eliminate per hour. This rate of elimination is constant and is independent of the total drug concentration in the plasma. So that makes sense to me. I don't know if that makes sense to you guys, but there's certain pills people take, and it is kind of has nothing to do with how much you're taking, and that's just an example. So the reactive concentration doesn't really affect the rate of that decomposition. So anyways, that's zero order. All right? What about this? So this, I'm trying to get you to understand what affects the rate here, not concentration. What about here?
Concentration.
And it's a direct relationship. Can we see that? Because it's a 1. And again, we're going to get into some sample problems here in a few minutes. But however this changes, your rate will change exactly the same. So this is a constant, so you can almost take that out. So K times A, no matter what A is, this is the same. It's a constant. So let's say K isn't there, your rate is directly dependent upon A. So if A is 0.2, then your rate's 0.2. Right? Again, forget K is there. If A doubles to 0.4, then your rate will double because it's a 1. So it's a 1-to-1 ratio. Does that make sense? I know it might be a little confusing. Obviously, I can imagine this in my head because I've done this, I teach this. You guys can't. But as long as you understand this exponent of 1 means it's going to directly affect the rate. What about this? Take the K out. Plug 1 in for A. What does rate equal? 1. Plug 2 in for A. So if we double the concentration, what happens to the rate? Quadruples, because it's a power of 2. You guys are all pretty good at math. Does that make sense?
Yeah.
So these types of reactions, that concentration really affects the rate. Okay? This is a 1-to-1 ratio. This is a 1-to-2, so it quadruples. Right? So it's like an exponential change. Does that make some sense before I get into some numbers? Yes, no, maybe? Okay. Let me get the graphs up here. And then I want you to, if you're running out of room, like underneath them, to write the graphs, then just kind of do it separate. But I'm going to show you 0 order graphs, 1st order, 2nd order. Make sure you label which one's which. All right? And then we'll get into some practice problems on actual reactions, actual numbers, and you're going to write actual rate laws. And again, what is all this about? It's if you can measure these concentrations in a lab setting, you can actually figure out how fast or slow it's reacting and what type, 1st order, 1st, 0, or 2nd. So just trying to make sure we understand what we're doing, not just getting through it for the test. All right, there we go. I'll just leave that up there. Tristan, lights please. All right, so here they are. Oops. I should have 2, 0. Where is that? I had it ready to go. Alright, so I'm going to show you there's 2 graphs for each one. 2 for the 0, 2 for the 1 1st order, 2 for the 2nd order, and it's because there is different units. Oh, take out your equation sheets. Go to the kinetic section. Alright, so here is the first order graph. Zero. Sorry. Here's your first zero order. Concentration versus time. I'll zoom in a little bit. I mean, it's pretty straightforward. So zero order graph, concentration versus time. What's the slope of that line? Tell us. Look at the rate law.
The concentration.
Here, maybe I'll show you this one. Here we go. I'll give you a different one. Which is kind of the same thing. Concentration of A versus time.
Was that A didn't affect it? The other thing, okay.
I'll come back to that. Write that down. Boy, now I can't see what I'm doing here. That's not the one I want. I want this one. Okay, this is first order. Write all that down. Concentration versus time. It's got a slope to it. Natural log of concentration versus time is a straight line. And the slope is negative K, the rate constant. Same thing with that first order. The rate constant is the slope. And the concentration of A versus time for the zero order, the slope would be your rate constant. On your equation sheet, there's, I think, 2 equations for kinetics. Does someone look quick?
Yeah.
Okay. Yeah, that's first and second order. They don't give you a zero. We'll write that down. I'll get to the equations tomorrow. Today, I just wanted to give you an overview of what each one kind of means, how to write the rate laws, sort of, generically. We'll get the graphs down, and then we'll have time to do one problem, maybe two, probably just one. One problem where I give you data, and from the data, you're going to write the rate law. And then, you'd be able to kind of sketch the graph. So, it's really important to remember the natural log of concentration versus time is a straight line, but the concentration versus time is going to be a slope. What does this look like that you've already learned? What type of graph? I'll give you a hint. The change in time is the same, but the concentration change, the change in concentration gets smaller and smaller. So you have a big change and the less. Carbon dating. Half-life. That's a half-life graph. Write this down near your first order. Half-life is an example of first order. It's first order, not zero order, even though it might make sense that it would be zero order. We'll talk more about that tomorrow, but it's because of this. The first order graph, this is a straight line, concentration versus time. First order, it has a slope to it. Again, we'll go over this stuff tomorrow a little bit more. All right, let me, where's my other one here? Second order is this one. Second order, concentration versus time, it's a slope again. But this case, over here, it's a positive K value, positive slope, and it's 1 over the concentration. So this says monomer. I want you to just use, what did you guys do for first order? What did it say? Did it just say concentration?
Concentration, Ellen.
Yeah, so just use the word concentration here. So keep them all the same. Concentration versus time, natural log of concentration versus time for the other one. 1 over the concentration versus time. This is a straight line, but it's a positive slope. So if it's a second order reaction, so obviously half-life is not a second order concentration. A second order reaction. And that's because the rate doesn't quadruple. It's a 1-to-1 relationship. Again, we'll deal more with it tomorrow. So I'm just kind of giving you the overview. This is what second order graphs look like. All three graphs, concentration versus time, they're decreasing. All. And the zero order was a straight constant slope. And zero order doesn't have, the zero order, both graphs are the same, concentration versus time. First order, it's a slope like half-life, but it's a negative constant slope for first order. And then for second order, it's a positive constant slope, and it's 1 over the concentration. Okay, so you guys have all the graph stuff? All right, so that was kind of the overview of everything. Now let's do a sample problem, and hopefully it makes a little bit of sense. Tristan Lights again, please. All right, I have 2 notebooks for this class, and I'm on the second notebook. That's a big day for us. Big day. All right, I'm gonna write a reaction on the board. I want you to, we are gonna write the rate law based on the data. All right, here we go. So we got NH4 plus NO2 minus yields N2 plus 2H2O. I don't think this is the same one in the book. It is not. Okay. All right. So, experimentally, 3 reactions have been observed. If the concentration of the ammonium is 0.1 for the first 2 and 0.2 for the third, sorry. Oh, well, alright. Technically this would be given to you. They would label that, this is the concentration of NH4 plus, sorry. And this is the concentration of NO2 minus. We got 0.010, 0.040, and 0.010. And then they would give you the rate. These are in molarity. And then the rate of the first reaction, if these are the concentrations of our reactants, the rate's been measured, again, experimentally, 1.2 times 10 to the negative third, 4.8 times 10 to the negative third, and then 2.4 times 10 to the negative third. I'm going to show you 2 ways to do this. Good, we got time. And then I will give you a couple practice problems for tomorrow, exactly like we're doing right here. You're going to be given data, and the question is going to say, what is the rate law? Then it's going to say, calculate the rate constant. So first, let's write the rate law. Okay. So, the way we do it is we see 2 experiments out of the 3, 1 and 2. This is held constant, but this changes. And we see in experiments 1 and 3, this is held constant, but this changes. So if we want to write the rate law, we're trying to figure out the exponents on the rate law by using all of these numbers. So if I look at the first 2 reactants, or 2 reactions, I see this stays constant, but does the rate change? Yes. So this is not affecting this rate. Only this is. And then if you look at experiment 1 and 3, this is staying constant. The rate is changing again, but not because of this concentration, because that's constant, it's because of this. So that's kind of the first thing we notice is which reactants, which reactions is one held constant and the other one's changing. One's held constant, the other one's changing. So what we ultimately want to do, I'm going to just write it over here, we want to figure out, all right, NH4 plus to the x, and then NO2 minus to the y. We're trying to figure out this exponent by using these numbers. Okay? So, anybody have an idea? How are we going to do this? Plug in the numbers. Can we do this? Can we say, all right, let's take this expression and let's plug in the numbers we have. And then K is constant, so I'm going to ignore that. So we're not going to use this. Let's take reaction 3 and divide it by reaction 1. So let's do this. We're going to take the rate, 2.4 times 10 to the negative 3 equals, I'm going to write this whole thing out, I'm going to plug numbers in. But I'm not going to write K because it's constant, so it's irrelevant. Hopefully that makes sense. I mean, I guess I'll put it in, but I don't have a number. NH4 is 0.2 to the x. NO2 minus is 0.01 to the y. I'm going to divide this reaction by number 1. So it's 1.2 times 10 to the negative 3 equals K times 0.1 to the x divided by 0.01 to the y. So when we do this, all right, stay with me, pay attention, because this is exactly how we do these problems every single time. You cross off what cancels out. This cancels out, this cancels out. That's just 1. This cancels out, this cancels out. That's just 1. So now we take 2.4 times 10 to the negative 3 divided by 1.2 times 10 to the negative 3. What do we get? Real quick, I gotta finish this, so just give me 30 more seconds. What do we get? 2? 2 equals, what's 0.2 divided by 0.1?
2. Point 0.1.
Type it in the calculator. This times what gives you that? 2. Thank you.
I said
2. Stay with me. Raised to the x. So what's x? 1. So with respect to ammonium, this is a first order. So we know x is 1. Now you do the same thing to find NO2 minus. Does that make a little sense? All right.
times.
I'm pretty sure she said 2 like